Hello, everyone. So, good morning, good afternoon, and also good evening to all of you. So, it is my pleasure once again to have Dana Bartosova of the University of Florida to give us a lecture on set theory. So, this is going to be the fourth lecture on set theory. And so, without further ado, I will have Dana taking over. It's all yours, Dana.
Thank you so much. Let me just share the slides, which means that I have to join on my iPad. And that means I have to find the link on my iPad, which I have just now. So almost there.
Sure.
How's everybody doing?
Doing good. It's getting a little warmer today here in Boston.
Here it's crazy warm.
That's good.
Yeah, so it seems that you need to make me a co-host.
Oh, that's correct. Let me
on the iPad, yeah.
So, okay, so you should be able to share your screen now.
Yes, perfect.
Yeah.
Okay. Here we go. Notability. Yes, perfect. There we go. So we can do a single page. Okay, so today we are going to talk about something that is more of applications of set theoretic ideas. It is related to set theory, it's related to ultrafilters, but the applications speak to a lot of people, and most of these results, they do not have independent versions, but you can also extend them beyond natural numbers. So this area is called combinatorial number theory, or also additive combinatorics. And it talks about primarily natural numbers, but often the proofs generalize to other types of, in this case, semigroups, or to larger systems than just countable sets. Okay, so what is combinatorial number theory? Has anybody heard about combinatorial number theory before? Okay, it's a good area. Okay, great. So please correct me if I say something wrong. It's a catchy name because it has number theory in it, so it's good to put it in your proposals when you're asking for something. So what is the problems that combinatorial number theory studies? And the cool thing is that it's really easy to say what the problems are, but not so easy to solve them. So combinatorial number theory is about finding patterns in subsets of natural numbers. So stereotypical question is, if I partition natural numbers into finitely many pieces, is one of those pieces going to contain some prescribed pattern? And those can be as simple as just x, y, and x plus y, or here I have an arithmetic progression of length c, or can I mix the operations? So here I'm looking at mixing the additive operation with exponential, but mixing the multiplicative exponential, but mixing the additive and multiplicative structure tends to bring some difficulties. Or we have density versions that became popular mostly in the past decade, but the first results go a lot further. So if I do have a partition into finitely many pieces, then one of the pieces has to be somewhat large. What if I have a different notion of largeness, and that largeness is going to be in terms of how frequent the numbers are inside from the set in initial segments of natural numbers. There's different types of density. We will talk just about the upper density. And again, does this necessarily need to contain a certain pattern? So for instance, I can have two subsets of natural numbers that are disjoint that both have positive upper density. Now, if I just look at that as a partition, then I will only know that a certain pattern by answering the first type of questions lives in one of the pieces of the partition, right? But now, if I do have a density result, then I will have it in both pieces if both have positive density. So this is a stronger result. And then this is something that ultrafilters have not really been that useful, but I have to mention it because this is definitely a very interesting and important subset of natural numbers, and this is the subset of prime numbers. So I guess everybody knows about the prime twins, and still an open problem whether there are infinitely many primes such that both the prime and p plus 2 is a prime. If you do not insist on the 2 here, then we actually know that there are arbitrarily large sequences that form arithmetic progressions, which was a huge breakthrough. But we cannot use the second type of result for that because primes do not have positive upper density. They are too sparse. And then last one that is a finite array, but still fits into this subject is when I have some set of size n or 2 sets. What are possible sizes for some sets? So if I take all possible sums from A, typically I exclude the A plus A. I want them to be different. So there has been a lot of research done on how large or small these can be, and bounds are easy to obtain, but questions of this sort. Needless to say that Erdős had a lot of and has still some of the open conjectures in this area. And then more recently, Terry Tao has been working a lot in the area. If you have any questions, as always, just please jump in at any moment. So, this is excellent reference, which for some reason didn't type as it should be. Excellent reference. Well, that's a new expression maybe. So this is not specifically a book on combinatorial number theory, but the methods that we will be presenting here all appear in there. It's a classic now in this field. I am citing here the second edition because this is the edition that is a lot cheaper, which is what the authors insisted on. The first edition, I don't know if you can still get it, but it used to cost around $350. And the second edition, the authors insisted that it's below $100, and it's about twice as thick as the first edition. So as you see, they talk about the Gemstone Compactification. Well, in Europe, we say Gemstone, in the US, we say stone Czech, which we talked about last time. So we will recall ourselves what the Gemstone compactification of a discrete set is. And if the discrete set comes with an algebraic structure, namely with a semigroup operation, then we will be able to extend that operation to the Stonechef compactification and use the compactness and existence of certain types of ultrafilters to prove some of these results in combinatorial number theory. How cool is that? So let's recall what ultrafilters were. Ultrafilters are maxima filters. So let's start with a filter. Filter is a collection of subsets that is closed with respect to upper sets. So if I have some A that is in the filter, then a larger set is also going to be in the filter. And let's remember that we think about it as a notion of largeness. So if a set is large, then a larger set should be large. And then we have closure under intersection. So if I have A and B in the ultrafilter, then also then also the intersection is going to be in the filter. And what makes it ultra is that it chooses about every set, whether it is small or large. So that means that either A or the complement have to be in the ultrafilter. And we know that these are maximal among filters. You cannot add anything more to it. to keep it being a filter, modulo this condition that we do not consider empty set being large. And we always have principal filters and ultrafilters. These are the ones that are generated by a given set, or in case of the ultrafilters, these are the ones that are generated just by one point. And we have non-principal filters and ultrafilters where this is not the case. And we talked about how we can get non-principal ultrafilters out of axiom of choice. And we will be talking about axiom of choice in particular, its equivalent formulation, Zorn's lemma, today again. So we will see some further applications. Any questions, remarks? And we have also put topology on ultrafilters, and compactness is going to be of benefit of us today a lot as well. So let's recall what the topology was, but we will not be proving again that the topology is Hausdorff compact. So it is going to be a zero-dimensional space where the topology is determined by a basis of clopin sets. And those clopin sets come from subsets of natural numbers. So we have a bijection between the subsets of natural numbers and these basic clopin sets. So for every subset of natural numbers, we are considering those ultrafilters that contain this set. So, in a way, quite simple. And let's recall that the closed subsets correspond exactly to filters. So we have that closed subset has to be an intersection of some basic closed sets. So we can think that we have intersection of these basic clopin sets. And that means that C consists of all these ultrafilters that contain all of these subsets of natural numbers that give rise to those clopin sets. And that means that if I look at the filter that is generated by the A alphas, then this is going to be the filter corresponding to C. Okay, so filters are dual to closed sets. Ultrafilters are points, which are of course closed as well. And we will also be using an abstract definition of beta n that we proved last time, and we will recall because we will be using it again today, is a universal property with respect to extensions of functions from natural numbers into compact spaces. So this is in general the definition of Gemstone compactification, even for topological spaces. Here, because we start with something that has discrete topology, we just talk about functions. So start with a function from natural numbers into K. You can always just think about it as a sequence that is indexed by natural numbers. These are the images, right, of natural numbers. And if I have any such sequence in a compact space, then this gives me a continuous extension from the space of ultrafilters to K. So how did it go? How exactly did it go once we do have the description of beta n in terms of ultrafilters, right? So why does beta n actually satisfy this? So we will take any subset that comes from that ultrafilter that we are trying to find an image in K. And we are going to find that as an intersection of some closed sets inside of K. In particular, we are going to look at these, as I wrote on the previous slide, KNs, right? The images of n that come with the indices from the set in the ultrafilter, and we take a closure. This is, of course, a closed subset. And since U is a filter, then these closures have to have the finite intersection property. Actually, even without the closures, this has a finite intersection property, so even more so with closures. Well, now, because K is compact, we said that the finite intersection property tells me that the whole family has to have a non-empty intersection. And it is straightforward to verify that because we have a maximal filter, then this intersection is going to be just a single point. And then we call this image of this is what I mean. The f image of u is also called the u limit of the sequence fn. So we will be using this notation in what comes. It's somewhat a shorthand to express this image. Okay, so now we will be using this extension property on n itself. And the function that we will be looking at is just going to be the addition on natural numbers. You can, of course, have multiplication on natural numbers, and that's going to work the same. In general, you can have any semigroup. So what is a semigroup? Semigroup is just a set equipped with a binary function symbol, which is interpreted as an associative operation, right? So how we think about dot, this is a function from s cross s to s. And to recall what associativity means, it means that if I multiply AB first with some C, then this is the same thing as multiplying A with the product of B with C. I don't necessarily have commutativity, right? So the order matters, but where I put the parentheses does not matter. Nevertheless, in natural numbers, of course, the order doesn't matter either. So now I'm going to consider the addition on natural numbers, and I'm going to extend that to beta n. So as I have plus from natural numbers to natural numbers, I can extend this to plus from natural numbers with beta n to beta n. And this is the starting point here. So I fix any ultrafilter here, and I'm going to say that n plus u is just shifting all the sets in u by n. So this is going to be the n plus a with a in u, and I might have to close under supersets, but to get an ultrafilter. So this is very straightforward. This comes just from the addition in natural numbers. What is going to be new is to try to say what the sum of two ultrafilters would be. So for that, we are going to fix this ultrafilter on the right-hand side. And now we are going to consider this function where we are in the second coordinate adding by this ultrafilter u. So that's going to be function from n here into beta n. So this is this function here. And now this is a function, and therefore we can extend this function to a continuous function from the Gemstone compactification to itself in this case. So we have a very special application of that extension property. And this is going to make beta n, of course, a compact space. And it is a semigroup. So obviously it's a binary operation. One has to verify that it's associative. I'll leave it as an exercise. And this right topological means that if I fix the second coordinate, right? So I have now plus that goes from beta n cross beta n to beta n. And if I fix the right coordinate, then this gives me this addition that goes from this first coordinate to here. And I want this to be a continuous function. Well, this is obviously a continuous function because I did specify that I want that to be a continuous function, right? This is this continuous extension. However, I could be greedy and I could want more, and I could want that fixing the first coordinate would also give me a continuous function, and there I would fail. So it turns out that I cannot extend in a way that I would have continuity in both coordinates. even less so wanting it to be continuous with respect to the product topology. So this is the best I can do. Of course, I could have gotten a left topological semigroup by thinking of fixing the first coordinate here, right? And then extending that, but then it would not be right continuous, right? So the choice I make is going to decide which continuity I have, and we will discuss briefly that we really do not have more than that. Any questions? Is this all old to you? Heard it 100 times. All right. So now we have beta n, not only very interesting set theoretically, but also algebraically and topologically. And we will see that on top of it combinatorially. And we will recall this explicit expression for the function extensions, which gives me a combinatorial description of this addition, right? So in terms of u limits, we have that u plus v is the u limit of the sequence of the function that goes from n into beta n, which is by fixing the v and running n over natural numbers, right? So this goes exactly with how the extension property worked into an arbitrary compact space. So now, what are the neighborhoods of u plus v? What are the neighborhoods that determine that point? So again, this is just application from the general case. A is going to be a neighborhood if and only if the set of n's such that v gets moved into that neighborhood by n belongs to u, right? So this is looking at my u plus v is supposed to be the limit point, and I have any neighborhood of that, and I'm saying that the elements in the sequence that I'm taking the u limit of, they are going to be inside of this neighborhood ultrafilter u often. Okay, so again, in comparison to the usual notion of limits, you would want that in every neighborhood the sequence hits cofinitely many times. Here, it doesn't have to be cofinite. It can be, it just needs to be from the ultrafilter. But the advantage is that now every sequence has a limit with respect to every ultrafilter. Okay, and this is just very silly when we are looking at this expression. It's sometimes useful to see it in different ways. So, well, what does this mean? This means that A is in n plus v, so we have that A minus n is in v. Okay, so we will use all of these as we please. So now let's just get a little familiar with how the algebra works. And this is what I was mentioning. The continuity on the left is actually never true, right? So I could say fix an ultrafilter on the left. When is this going to give me a continuous function from beta into itself? And it never does unless I started with a principal ultrafilter. So unless I started with an element of natural numbers, then I already lost continuity. And it's actually easy to show that this left continuity is equivalent to being in the center, so commuting with every element. And again, that means that the elements of beta n that commute with every element are only the natural numbers themselves. So the center of beta n is n itself. We will not need that too much. We will need a continuity with principal ultrafilters a little bit. It's that is straightforward, that holds. So it will be easy to remember. And we will use this notation to save some space, but this is also a notation that's very traditional. So you could see in star in set theory in two meanings. Here we mean the non-principal ultrafilters. If you have two non-principal ultrafilters, then you cannot get as a sum of those a principal ultrafilter. So they also form a compact semigroup. Well, they also have the semigroup structure. They are closed under the operation. The compactness follows from the principal ultrafilters being isolated, right? So every principal ultrafilter is an open set, obviously, right? Because it's you have the closed set that corresponds to the filter generated by the singleton. Therefore, natural numbers form an open subset of beta n. Therefore, if I take that out, it's going to be closed and therefore compact. So this itself is a compact and of course, right, topological semigroup. And it turns out that this is really a mix of algebra and topology. Some things you get from the algebraic structure, some things you get from the topological structure. There is a general theory of compact one-side topological semigroups, and we will mention some of these results. We will need to extend this the operation to other semigroups, only semigroups that are related to, and in particular, we will be looking at this semigroup. But it doesn't hurt to say that nothing really changes. So n is our most important example, and a lot of work is done for natural numbers first, just because we care. But many of the results can be developed for an arbitrary semigroup, in particular if they have at least some cancellative properties, which these all have, or if they are a group like integers or, well, rationals, real numbers are actually groups. So you can develop the same theory, you can just extend the operation in the exact same thing and get a compact, right, topological semigroup. So there is nothing special for n. There are some results where it matters whether your semigroup is countable, whether it has some cancellation properties, and whether it's commutative, for instance, or amenable. There are some results where you do have to restrict yourself, but the theory that we have so far developed holds everywhere. And one disclaimer is that the world is much more colorful than one would at first guess, and that is that if I take ultrafilters on n cross n, this is very far from ultrafilters on n in two coordinates. So this is something that I'm particularly interested in. There is not too many results about that. So I think this is an interesting research direction also because we are lacking results. There's relationships to topological dynamics, and there are some fun results about existence of certain ultrafilters telling you how far these are. It's related to p-points that we talked about last time. So I'm going to mention open problems related to this difference in the next lecture. So maybe you will have something to work on. Any questions so far? Okay. So now we are getting to one secret that is going to help us obtain those patterns. So we are going to find magical ultrafilters that are called idempotent ultrafilters. But as I said, some things are not really all that about beta n or beta anything. It's about compact right topological semigroup. So every compact right topological semigroup contains an idempotent element. That means an element that multiplied with itself is just itself. Of course, beta n contains idempotent. It contains 0. I do consider 0 a natural number, but that's where we restrict ourselves to n star, which is still a compact right topological semigroup, and we will get a non-principal idempotent, which is already an interesting one. So this is actually a very simple lemma, but the applications are plentiful. So we can prove it on one slide, half of the slide, and we will employ Zorn's lemma and then use the algebraic and topological structure. So this is sort of a show off of how the set theory, topology, and algebra come together in one proof. So first of all, we are going to establish that there must be some minimal closed subsemigroup. Well, if I do have an idempotent, then an idempotent is a subsemigroup, right? Because subsemigroup only needs to satisfy that it is closed under the operation. So if P times P is equal to P, then the singleton P gives me a semigroup. It's going to be closed only everything is Hausdorff. So T1, that means points are closed. So it will be, and it's minimal, right? There's nothing non-trivial below it. So I will first establish that a minimal subsemigroup exists, and then I will show that it has to be just a singleton. So if we want the minimal element or maximal element, as we had it phrased last time, then we can turn ourselves to Zorn's lemma. So here we are going to use it in a flip direction. Last time we were talking about chains having upper bounds, and then the poset having a maximal element. Here, the order is more natural to consider, well, the order that we naturally consider is requiring the dual of Zorn's lemma. That means you take Zorn's lemma and flip it upside down, right? So we can always do it with a poset. If I have a poset and I'm just gonna say, I'm gonna create a new poset by saying that the relation is opposite. If P was smaller than Q in my poset P, the flipped poset is going to say that Q is smaller than P. So now maximal elements become minimal elements and upper bounds become lower bounds. So of course I could also say I'm just going to think of the poset with respect to the flip relation, but that's not really natural. So this is the natural way to phrase it. So I will consider the poset of all closed subsemigroups of S, and I want a minimal element. So I'm going to consider any chain of closed subsemigroups. And then I claim that the intersection is a lower bound. Well, if the intersection is non-empty, then of course it is closed under the operation, because that's a finitary thing. If it were not, then it would have to have failed somewhere in the chain itself. And it's going to be closed because it's a chain. That means that it has the finite intersection property, right? Because intersection of finitely many things is going to be the smallest element of the chain. And because we are in a compact space, then the intersection is going to be non-empty. So now by Zorn's lemma, I have a minimal element, right? The dual of maximal element. Now we have to show that this minimal element is just a singleton. So we are going to employ minimality and continuity. Okay, so we fix some P inside of M, and by continuity on when fixing the right-hand side, right? We have a right topological semigroup. We have that M times P. So this is an image of a compact space. This is compact. So this, and therefore it's a closed subset of M, and it's also a subsemigroup. Why is it so? Well, if I have anything in M times P, then it is of the form N times P. So then if I am multiplying with something else, then this is M prime times P. Well, but P is from M, right? And M is a subsemigroup, right? So this is from M, and therefore this is from M. So I again have an element that is from M times P. So I'm inside of here. So this is a subsemigroup of M, but M was minimal. So it has to be M itself. Okay, so we have employed continuity and minimality, and we're gonna do it again. So now if it's M itself, then M times P has to contain P because M did. So we're gonna look at all those Q's, thinking about M here, all those Q's that map P to P. And this has to be non-empty by this equality here. And this is again going to be a closed subsemi group. Well, it's easy to see that it is a subsemi group. Why is it closed? Well, it is the preimage of P under the map multiplication P, right? So I have a multiplication by P. This is a continuous map from M to M, right? And then I'm looking at the preimage under this map of the singleton P. P is closed, and therefore the preimage is closed as well. Now, by minimality again, N has to be equal to M, and therefore P has to be in N. But that means by the definition of N that P times P is equal to P. And then by minimality, that gives me that M has to be just a singleton P. Okay, isn't that cute?
Yep.
Okay, great. So we will see that the idempotents have a lot of power because the sets that are included in them, it's sort of hard to move them away from the idempotent ultrafilter. So we will see an application. But let's start our search pattern by where a lot of it really started. So nowadays, I would say that we can think of these results in combinatorial number theory as Ramsey phenomena. It's true that some of these patterns results are before Ramses Theorem. Ramses Theorem is from 1932. This is the original version that was proved with an application in logic. So this was more of a technical lemma, but Ramses theorems in general look for patterns. So sort of say that if you are in a large space, large universe, then you're going to find a pattern that you were hoping for. And if we think about Ramses theorem in dimension 1, then it has exactly the statement as we started with on the first slide. So we partition natural numbers into finitely many pieces, but this time we are not actually requiring any structure on n. So we are not interested in algebra. We are just interested in sets, and that's a good warm-up because it's a lot easier. So then obviously one of the pieces is infinite, because if I have finitely many finite sets, the union has to be finite. So this is easy in dimension 1, but it turns out that this is true for arbitrary dimension. So let's say that K is finite. When we go to infinity, we have to be careful. So K is finite, and we look at K element subsets of a set. Here we will look at natural numbers again. So now we are not going to partition natural numbers, but the K dimensional analog of K element subsets. And then we claim that there is still going to be an infinite subset of natural numbers, such that all K element subsets of that are going to have the same, are going to be in the same part. So I will be going between colorings and partitions, which is the same thing, right? If I have a partition, so let's say here, then I can match this with a coloring from natural numbers into the parts, right? So 1, 2, up to n, and I'm going to say that C of n is equal to I if and only if n is in Pi. And if I have a coloring, I can look at pre-images of the colors, and I'm gonna get a partition of natural numbers. Okay, so I can go back and forth. If my PIs are not disjoint to start with, I can disjointify them and everything works the same. So really, these are the same notions. Okay, so if I partition n to k into finitely many pieces, then one of the pieces is going to contain all k element subsets of some infinite set. So, you can just think for a moment how you would do it even just for pairs, right? How would you force all pairs of some infinite set to be inside of some partition, right? Let's say I have a partition into 2 pieces, and I would like this to be in my set, right? And then, okay, I can, of course, one of the pieces is going to be, well, okay, if I have an, each of these PIs is going to, so at least, okay, at least one of the PIs is non-empty, right? So it's going to contain some pair. So, okay, I can get two things. Now, how do I get infinitely many? Now I could, what if I have a third element? And then let's say that the first and the third are in this piece of the partition, but the second and the third are actually in this piece of the partition. So it starts being not so easy. And it turns out that it's even when you restrict yourself to finite version of this, it is not absolutely constructive. You cannot just sit down and do your best, because you would run out of time. Okay, so how do we prove this? So here we are going to prove it by induction on the dimension. I'm only going to do the step to dimension 2 because it's a little easier, but if you go from dimension k to k plus 1, it really is the same thing. And you can do it without the use of ultrafilters, but this is a warm-up for how we can use ultrafilters. So here, we are using the ultrafilters minimally. We are not using the additive structure of the ultrafilters at all. Basically, we are actually saying something a little stronger than this theorem looks like, right? We are gonna say that if I take any infinite subset of natural numbers, then on that infinite set, I'm going to find a further infinite set such that all of the k element subsets are going to be in one piece of the partition that I started with. So the ultrafilter is just going to sort of make sure that the sets that I am working with, by being in the ultrafilter, they are still infinite. So that's why I'm choosing a non-principal ultrafilter. I just want to make sure that I still have enough choices. And because I will only be making finitely many choices in my construction, in the previous step, that I still have infinitely many choices to choose from. So this is one of the standard procedures when you are raising dimension, and that is that I'm going to reduce the dimension. So I have dimension 2. So how do I reduce it to dimension 1? Well, I'm going to, excuse me, for each L, for each natural number L, I am going to think that L is my first coordinate, and I am going to have the second coordinate run over natural numbers. This is going to give me a coloring on natural numbers. So I'm going to color by the same number as I have the pieces of partition, and I'm going to say that M has the color I if the pair LM is in the piece PI. So now I am in the first dimension, and therefore I know that one of the pre-images of the colors has to be infinite, right? This is something that that I have from the first part. But not only infinite, I know that the ultrafilter has to choose one of them, because ultrafilter always has to finite cover of natural numbers. So there is going to be some set in the ultrafilter that is going to, where all elements of that set are going to agree on the color with respect to this L. And I'm going to remember the color. So I'm going to call the color DL for each L. And now this is the split into the two dimensions, right? So now I was fixing the first coordinate, and I was looking at colorings for the second coordinate. And now this gives me in turn coloring on the first coordinate, which is again dimension 1 only. So we get this coloring C, where I'm going to choose the color to be the color that the second coordinates for L we're choosing on a set in the ultrafilter U. So now I am going to choose a set from the ultrafilter now with respect to this coloring. Okay, so again, the pre-images of the colors of this new coloring they cover natural numbers, obviously. So one of the pieces has to be in the ultrafilter. So now I'm going to start building my set Y. So I'm going to start with some arbitrary A0. It's not going to be important. What is important is it is from this C. And then, well, what it means that A0 has the color J, which is its DL, together with every element that is in DA0. So now I'm going to choose something from this DA0, which however is also in C, so that it's going to cohere as we go on. And I don't want repetitions. I don't want to be picking 0 over and over again. Well, actually, I don't really. Yeah, okay, I have that in A0, but I don't really have it in the A0, so I'm looking at just subsets. So it's a little redundant. So this has to be in the ultrafilter again. So what I'm using is that if I have two sets in the ultrafilter, intersection is in the ultrafilter, and because the ultrafilter is non-principal, it is infinite, right? I will be able to always choose. Now, if I have chosen some elements already, then I'm going to choose the next one. And well, it's infinite. So if I take those elements away, it's still going to be infinite. So it's going to be in, and it's going to be in the ultrafilter. Otherwise, a finite set would get in there. And then for each of the elements that I have already chosen, I want to make sure that the next one I choose is going to come from the sets where I have the correct color. So I'm going to take the intersection of all of these DS's that I have already, that I'm already considering. And this is still going to be in the ultrafilters. There is space for this new AS plus 1 to come from. So now I say that Y is going to be this set A0, A1, and so on. I can proceed by recursion to define this set, and I can inductively show that this works, but I think it's quite clear by now. Any questions?
Sounds good.
Okay, so you can think a little bit about how you would bring it to a higher dimension, but you do the same thing by just saying, I'm going to forget or not forget. I'm going to let the last coordinate to be free and fix an orthogonal, right? And color according to color natural numbers according to how the last coordinate moves. And that gives a coloring on our tuples, and then I diagonalize through there. So it's a very similar idea. And again, theorems, they typically have different proofs. A lot of them have very similar features. So you always have to work. And then you have the theorem because it's new proof, but the way you do them has some similarities. Okay, so let's move on to one of those patterns that we talked about at the very beginning, and these are arithmetic progressions. So an arithmetic progression is an arithmetic progression. It means that I have an element that is my starting point, and then I'm going to take in equidistance further elements, right? And depending on how many I have, that's the length of my arithmetic progression, right? So I have it based here at my at some number a, and then I have a plus d, a plus 2d, up to a plus a minus 1d. You can, of course, define also infinite arithmetic progressions, but it turns out that this is too much to ask. So if I have a partition, finite partition of natural numbers, then one piece of the partition has to contain arbitrarily long finite arithmetic progressions, but we cannot get an infinite one. So I could also phrase it differently, saying that for every k, one piece is going to have an arithmetic progression of length k, but it turns out that you can be more demanding, and that is you will have one piece that is going to contain all of them at the same time. And this is a trait that happens when you use ultrafilters. Okay, so maybe just to digest this theorem. So has anybody seen this theorem before? It's very old, so nothing new. I believe it's from 1928, and the original proof doesn't use ultrafilters. Ultrafilters give you a simpler proof and some insight into how to use ultrafilters, and also into classification of what subsets of natural numbers do contain arithmetic progressions, right? Because now we are saying that the piece of a partition, but there is actually a more cleaner way to say which of the pieces it's going to be. So suppose that I'm partitioning only into two pieces, right? So my natural numbers is into two pieces. So that means equivalently that I have a coloring of natural numbers by two colors. So now, can you find a monochromatic arithmetic progression of length 1? Well, I can imagine you're as tired as I am. So, or just thinking that this is a very silly question. So of course, one of the pieces has to be non-empty, and arithmetic progression of length 1 is just a single element. So done. Well, for 2, it's not a lot harder, right? Because I do have to have one of them actually infinite. So I do definitely contain two elements. And then if I have any A, B, setting if B is greater than A, that this is equal to, D, B, setting D to be equal B minus A, then I'm done. So nothing smart. But for the sake of time, I'll leave you with the arithmetic progression of length 3. It is something that you can do just on the paper, hands on. So it's fun. Now, it's also a good idea to ponder about why cannot I upgrade to infinite? Can you give me a coloring? And actually you can do it with two colors only, or split natural numbers into two pieces such that neither of them is going to have an arithmetic progression that would be infinite. How do I kill an arithmetic progression? Maybe I shouldn't be talking about murder in something that's recorded. How do I ensure that I cannot keep going with a certain distance in one piece?
Just alternate?
So if you mean just the 1, 1, 1, 1, you mean 1 and then the other ones? Is that what you mean?
Yeah, that's what I was thinking.
Right. So then you would have, evens and odds. These are arithmetic progressions, right? With the distance 2.
Oh, yeah.
You do want to alternate in some way, but you want to alternate in a way that you're having longer and longer intervals of one color, right? Because then there is no way that you can continue with the same distance forever, right? So I'm going to do this, and then this, and then this, and so on. And I'm going to leave the same spaces for the other one. Exactly. And, this is actually tightly connected to topological dynamics, or these sets have meaning in topological dynamics. And it turns out that the thinking about beta and as a dynamical system gives you sort of classifications of these sets where you can find patterns. So it's even more interlaced between areas than we have discussed so far, but this is a whole other discussion to have. So where can we find these arithmetic progressions? And for that, we have to develop a little bit more of a theory of compact, right, topological groups. The proof itself is not too hard once we have these basics done. So in any semigroup, I can talk about ideals. So ideals, this is a notion that you can equate it to thinking of normal subgroups. So an ideal is in a semigroup is something that is itself a subsemigroup, but also no matter what element from S you multiply it with, you will stay within, right? So in other words, this condition reads as for every S, well, S1, S2 in this case. Let me write it slower. For every S in S and for every I in I have SI is in the ideal and IS is in the ideal, right? I contract under. Of course, so that I have this inclusion here. If I am in groups, then this is not going to, then in groups only the whole thing is an ideal. But in semigroups, this is a very non-trivial notion, and beta is very far from being a group. And then if I am only restricting to one side, so that is that I am running over S on the left-hand side or on the right-hand side, I get a notion of a left ideal and a right ideal. And of course, these are not necessarily the same. We said that beta is very far from being a commutative semigroup. So now, if I have a compact right topological semigroup, then it's going to have minimal left ideals and they're going to be closed. So here I have the closedness and left together, and this is because we are talking about right topological semigroup. If I had left topological semigroup, I would have closed right ideals. It turns out that again, I cannot get all of it. So in right topological semigroup, I cannot have minimal closed right ideals. Okay, so this is now a mix again of the minimality and continuity, similar to in the LS lemma. So if I do have a minimal left ideal, then I'm going to show that it has to be closed. So suppose that I have a minimal left ideal and I choose an element from there, then I do have right continuity. So fixing S and running X and running over S. This is a continuous function from S to L, right? Because I have a left ideal, so the image is under L. And as it's continuous, L has to be compact. Right, so I had L being image of a compact space has to be compact itself and therefore closed. So now when I'm looking for a minimal ideal, I know that I can look only among closed ones. That's where I can use Zorn's lemma being in the in a compact space. So now I have a poset of all closed left ideals. Before I had closed subsemigroups, so now I have a little different object, and ideals are in general larger than semigroups. The subsemigroups only have to be closed under the operation. Here you have to be closed under multiplication from anything from S. So now I have a poset of closed left ideals, and then if I have a chain, then the intersection is also going to be a closed left ideal. So again, straightforward. So then I have to have a minimal element, and I'm done. Okay. So this is one more slide where we talk a little bit about ideals. So if I have minimal left or right ideals, then they have to be disjoint, right? Otherwise, the intersection would be again would be a smaller one, right? So they have to be disjoint, and if we think of beta, then there is going to be a lot of them actually. And if I intersect, so it turns out that minimal left ideals and minimal right ideals always intersect. And their intersection is actually a group, right? And we know that every compact right topological semigroup contains an idempotent. L is closed, so it's compact, and it's a subsemigroup. So L contains idempotents, and this intersection, being a group, is going to have as an identity some idempotent inside of L. So we don't need to use that specific information, but we will use idempotent from L. And then more importantly is that we also have a minimal two-sided ideal, and that minimal two-sided ideal can be described in two ways, well, three ways really. So it's an intersection of all ideals, both-sided ideals, but it's also a union of all minimal left ideals and all minimal right ideals. So obviously every both-sided ideal contains minimal left ideal. We know that we have minimal left ideals, so the two-sided ideal also has to contain some. But then if I multiply the left ideal on the right-hand side, if I have L, I know that SL is below L. So if I multiply it again by S, I get a both-sided ideal, right? So and it turns out that this contains all minimal ideals. So they cannot be disjoint, right? Minimal ideals cannot be disjoint, unlike minimal left or right ideals. Okay, so this is how they look. And then we need some information. These are all straightforward lemmas. If I can embed a semigroup into a compact semigroup, so think of natural numbers and beta n, but we will have a little bit of modification of what my semigroups are. So if I now have a subsemigroup of S, then I can look at its closure in T, topological closure in T, and it turns out that it's still going to be subsemigroup. So the right continuity is going to be enough. And the fact that elements from the semigroup itself give you also left continuity. And if I have an ideal left, right, both-sided of a subsemigroup, then closing, I'm sorry, this is I, this A is I. Then if I close that inside of T, then this is of course going to be below the B closure, but it's still going to preserve the algebraic property. So it's still going to be left respectively right or both-sided ideal. Okay, I will recall these as we use them. This is just to have them in one place before we use them. And let's not forget what we were proving, Thunderbirds Theorem. But before, are there any questions? So we have Thunderbirds Theorem. And we will actually see that again, these PIs, similarly to the counterexamples to Thunderbirds Theorem, the ones that satisfy to infinite version, the ones that satisfy finite version, they also have a further meaning. And it turns out that you can choose a PI, or that any PI that belongs to an idempotent in a minimal left ideal is going to work. So actually, it doesn't even have to be an idempotent in this case. So any element, any ultrafilter that is in a minimal left ideal will have the property that every set in that ultrafilter is going to contain arbitrary non-finite arithmetic progressions. And if I have a partition of natural numbers, of course, one of the pieces has to be in the ultrafilter, so it's going to prove our theorem. But really what I'm saying is that any element of a minimal left ideal is going to satisfy having arithmetic progressions. So we want this for all case simultaneously, and it's going to be the case because we are going to use this U for all of them. and it chooses one of these PIs. But we will show that it works by looking at each of the case separately. So it is straightforward from what we just said on the previous slide, that I can compactify n to k by looking at its inclusions coordinate-wise into beta n to k. We said that if we look at beta of n to k, which would be this Thunderbirds compactification, this is not the same as beta n to k. But it is still a compactification. So I still have n to k in here with a dense image. It's just not the maximal compactification, but it is the one that serves our purpose. Excuse me. And I'm going to, in n to k, look at all possible arithmetic progressions, right? So I'm looking at all possible bases and all arithmetic progressions. That means that we do not want to repeat a indefinitely, so we do not allow zero distance in here. But then we will also define something bigger, and this is technical because that's what gives us the proof, and that is that we add to it also those constant sequences. So we have the arithmetic progressions, this is what we really want, and then it turns out that we can show that this E is a subsemi group, obviously. And therefore the closure by the previous slide is a subsemi group of this beta n to k. And then it turns out that I is an ideal in E. And again, by the previous slide, we have that the closures are also ideals, right? So here the closures are in the compactification that we are interested in, which is this one. Okay, so we have n to k, then we look at I, which is the all the arithmetic progressions. So this is where we are trying to find our solution. And we look at a bigger subsemi group of my semigroup that I started with n to k. And now I compactify and I look at closures inside of there. So now I'm going to include my my ultrafilter U in here. So what I want to show is that this this subsemi group, right, of beta n to k contains the constant sequence of only U's, right? And this is for U arbitrary element of a minimal left ideal of beta n. So how do I know that something is in the closure? I know that if every neighborhood of the point intersects something in E. So let's take a neighborhood. Well, that neighborhood, it's coordinate-wise. We're looking at the product topology in here. So in each coordinate, I have a neighborhood of U, which comes from element of the ultrafilter, right? I have these clopin sets that are given by subsets of the ultrafilter. So now, because they all come from the ultrafilter, then their intersection has to be in the ultrafilter. In particular, it's non-empty. So we often use the infinity or the infinity in the non-principal ultrafilter just to have something non-empty. And then if I take any A from this intersection, then I get that the constant sequence is going to be in E, right? Because I did put all of them in here. So this is the technicality. Any questions? Right, so I needed something from E to B inside of every neighborhood of U, but of course, there's going to be a lot of them. And then we actually will have that it's also going to be in that ideal. Okay. Okay. Because the closure of I is a both-sided ideal, and then it has to contain any minimal left ideal of E, and in particular, okay, I see this. This is going to be inside of I-bar. I'm not sure what happened in there. Right, so the minimality of U, so coming from a minimal left ideal, is going to ensure that if I take this k-dimensional fold, then because this element is inside of E bar, then this is going to be an ideal left, minimal left ideal of E bar, and therefore it has to be in the both-sided ideal. But then we are done, right? Because then it tells me that there is a neighborhood of this element U, right? That gives me that this thing itself is in the ideal, and therefore it has a neighborhood that contains an arithmetic progression, and therefore it finishes the proof. Okay, so this is somewhat stronger than seemingly what the Thunderbirds Theorem is saying at the beginning, and that is that I can exactly describe really the sets Pi that contain arbitrary long finite arithmetic progressions, and there is really an abstract description just by saying it's a little lengthy, but it basically says that it contains arbitrary long sequences that have bounded gaps in between them, which doesn't necessarily need to be equidistant gaps, but it turns out that this is enough to get also equidistant gaps. Okay, these are called piecewise synthetics if you're interested. So let's move on to the next pattern that we talked about, and that was now a pattern where you can also think about it in a way as an arithmetic progression of length 2, but with a distance in it. And you know, that doesn't look so impressive, and it's also from the 19th century, and it has finite versions as well, which means that you would not necessarily go to all natural numbers, but just some finite segments, so then it looks a little more impressive. So if you partition natural numbers into finitely many pieces, can you find x, y, and x plus y in one of the pieces? Can you? Okay, so you're gonna tell me on Saturday morning, okay, but you really need only, I think, first 5 natural numbers or 7 to show that every partition of that into 2 pieces is gonna give you that. Now there is a more impressive version, and that is that not only you can find this pattern of length 3, you can actually find, instead of just xy, a finite set of size k, such that all finite sums of different elements are going to be in there. Okay, so instead of just x, y, and x plus y, I might have x, y, z, and x plus y, y plus z, x plus z, and x plus y plus z, right? And it keeps growing. So this is the notation for the finite sums. This is the set of all finite sums of distinct elements of AK. Really, here we only have finitely many things, and if we do not let them to repeat, right, and I really have only finitely many summands. But we can actually generalize that to an infinite version. So, and therefore, these finite versions are going to follow. But these are historically important because, of course, these were first, and they had purely combinatorial proofs, as did Hindman's theorem. So Heinmann's theorem also originally had a combinatorial proof. But if you use ultrafilters, then it boils down to only a few lines, as we will see. So just the notation again, that we are looking at finite sums of distinct elements from a set, so for arbitrary set. And now Heinmann's theorem says that if we partition into finitely many pieces, then one piece of the partition is going to contain an infinite subset. Let me maybe write it down here, infinite A, such that all finite sums of elements from A are going to also land in that piece of partition. So now that sounds a lot harder to do by hand, and it indeed is. But the ultrafilter magic really works its way here. So we will be using idempotence here, right? And by Ellis-Numakura theorem, we know that because n star is a compact right topological semigroup, it does have idempotence. So we have non-principal idempotent ultrafilters. And again, as in Thunderbirds Theorem, it turns out that this one piece of the partition is actually picked out by some element of Gemstone compactification that has a definition, in this case, algebraic. So every element of every idempotent is actually going to contain a sequence whose all finite sums are contained in that set. And it turns out that this actually tells us how or what sets idempotent ultrafilters are built out of, because it also goes vice versa, and that is that idempotents have that a set is in the idempotent if and only if it has such a sequence. Okay. So now again, we have this case that because idempotent has to choose one of the PIs, this is what proves the theorem. So we will prove this version right away. So this is what we are proving, that if I have an idempotent non-principal ultrafilter and I have set in the ultrafilter, then this set is going to contain an infinite subset whose all finite sums of distinct elements is in that set. And I'm going to use this notation A star that is going to specify all n's outside of my set A such that n plus u is in the neighborhood specified by A. This really makes sense for idempotence rather than for anything else, because we are going to use that this is also in U, right? So this recall, right, that B is in U plus U, right? And now we have that this is it, this is equal to U, right? So we have that B is in U if and only if the set of n's such that n plus u is in B bar is in U, right? So now we are using that because this set is in U and my original set is in U, then the B star, right, which is really the intersection of B with, let me say, RB. There is a reason for that, because again, it has a dynamical meaning. Then this also has to be in the ultrafilter, right? So that's where I can say that I'm only going to fish for these inside of the set that I started with. Okay, and obviously this is a subset of A. So let's have what we have. We have the idempotent, we have a set in it, and we are going to construct our sequence. So let's take A0, an arbitrary one from A that also satisfies that it has to bring A back inside of U, right? Remember that this means the same thing as a member of n plus u, which means the same thing as A minus n being in U. And now we have that, A star is in U, and then by the choice of A0, also A star minus A0 is in U. And then I can intersect with A star, they are all in U. So this is still a member of U. And then I'm going to choose A1 out of this set, out of this intersection. And then obviously A0 is in A. That's what we choose it from. A1 is a subset of A, so it's also in A. And A0 plus A1 is going to be in A star, because here we have that the elements of A1, I mean, if I take an element from here, which is, A1 is from A star, and I take, sorry, what I want to say is, right, because I took A1 from A star, then I have that A1 plus A0 is in A star. Okay. So now we will just go with this process. So we are going to construct these guys, and I want that all the finite sums are going to be inside of A star. And I'm going to build the next one. So the next one is going to be again in the A star. So that's for compatibility with A0. And then I'm going to look at all the finite sums. So these are all the things that I want to be adding an plus 1 to, and still keep inside of A star. And I'm going to look at this shift of A star minus S, which by the previous definition, right, of how I'm building the sequence, these are all going to be in the ultrafilter, and I'm taking a finite intersection, so this is still going to be all in the ultrafilter. And then by the definition, I get that okay, I'm sorry, I think I did not, this really doesn't need to be there. Then just the sequence of these ANs is going to work. Right, so I do a recursive definition, and in each step I verify that I haven't got outside of A star. Any question? I was first writing a slightly different proof, which is a little longer, and I would come out of the slide. So this is a little more space consuming one. Okay, so this is a very nice theorem. It has some generalizations. I will talk about one of them. But also, we can prove finite versions of Ramsey theorems out of infinite ones. Of course, finite people like to prove finite theorems directly, right, without going to the infinite ones. Also, because of this little thing that for ultrafilters, you do need axiom of choice, and typically for these theorems, if you analyze the proof, no axiom of choice is needed. But hey, it's better to have some proof than to have no proof, right? So we'll still take it. And this compactness principle is used all throughout. You might have heard about it in your lectures on model theory, where you can find a model of a set of sentences if and only if every finite segment has a model. So this is in that vein. So what we can get, so this is an example of Heinmann's theorem that is more quantitative, a finite version of that, where we use a non-principal ultrafilter to show that if this finite version was never true, then we would have bad colorings at every finite instance, and we could glue them into a bad coloring for all natural numbers. So what is a finite version? Well, finite version is where we are not necessarily coloring all natural numbers, but just find some finite piece. But we want to know that we are going to have in one piece of the partition the finite sums of some sequence of length k. And I also am now a little careful about how many pieces of the partition I have, right? Before it was no matter how many, as long as it was finite. But now the choice of how far in natural numbers I have to go to satisfy this partition theorem does depend on how many pieces I have. So now I have to quantify over that as well. So for every k, for every m, there is some natural number n such that no matter how I partition it, and here I'm identifying n with 0, 1 up to n minus 1, as we usually do in set theory. There is some piece of the partition that is going to contain finite sums of some set of cardinality k. Okay, so we go by contradiction, which may be somewhat counterintuitive, but we are not proving the theorem directly. We are just proving that the infinite version that we already have does imply the finite version. So if this is not true, then any natural number fails, right? So for any natural number, there is a coloring of what on earth? Oh yeah, I know what happened. This is n minus 1. So for any natural number, I can color it by m many colors so that no pre-image of any of these colors contains these finite sums of a set of size k. So this is what I mean by bad coloring. It fails the theorem. And here I'm phrasing it with colorings because I somehow feel like it's just so much easier to write than partitions. So partitions are good for something, colorings for other things, they're the same. So now I'm gonna glue them along some non-principal ultrafilters. So again, what I need from my U is that every set is infinite. And I'm going to construct this coloring by saying that L, natural number L, is going to take color I if and only if the n's such that the bad coloring at n thinks that L should get color I is in U. And this is also always going to happen for some I, right? Because when I look at it, I have for each I can look at all those n's such that C and L, or let's say for J, so that we are not repeating, right? And I'm gonna run through the colors. Well, this partitions natural numbers, right? Because every n, every coloring corresponding to n does have an opinion about what color L should get, right? So this covers all natural numbers, right? This is a partition of natural numbers. And therefore, one of the pieces, which I'm going to call AL, has to be in that ultrafilter. So now we know that the infinite version works. Oh, I'm so sorry. You know what? It is very late. So I was proving this in my head in the car for arithmetic progressions, but then I realized that I wrote it for Heinmann's theorem. So now it's a mix of the two. So, but anyway, so let's assume that this does contain, well, it actually contains an infinite set. So we can take first Heinmann members. So it contains A0 up to a k minus 1. I feel like something didn't compile. Oh, it's below, it's not visible. Okay, well, we'll recreate it. It's finite sums of that, right? This is all contained in here because we know that this is the case. So now I'm going to look at for each of these AIs. Take the corresponding AI, right? So this set is what decided that this is going to get the color I. This is a bad notation, J. Because the color I is not related to that, right? So for each element of this, I'm going to take this thing that that decided that, and I guess I actually want this for each of the elements from here, right? So for each actually X in here, I'm going to consider that. That's right. I have to improvise. So then there is only finitely many of them, right? Finite sums of a finite set. There's only finitely many. I'm not repeating anything. So it's only finitely of those. So then if I look at the intersection of these AXs as X runs over these finite sums of the AJ. Well, then this is in the ultrafilter. And these are the indices N that are going to think that all of these X's should be getting the color I. But this is a contradiction, because if I take any N inside of here, then it says that the Cn was not a bad coloring to start with, right? Because this exact set is going to be monochromatic with respect to Cn. Any questions? I'm sorry for the mix-up. It seems that I did not delete this part, and I did continue writing. So it's there. Okay, so this is what I want to say is this is just an example of how you can glue bad colorings, but it's a principle that's used very frequently. So it's a neat idea that can show itself very useful. Okay, so let me now just go through a few results without a proof, just to show how versatile this is and that it reaches out to other places, and where being open-minded about learning things from different areas help people, and as you see, very, very famous people prove substantial theorems. So people are not afraid to go into ultrafilters and into ultrafilter combinatorics and algebra, even if they are coming from very different areas. So, well, we know Gowers is very versatile, and some of his results are in functional analysis. So I will just talk about the space C0, which is the set of sequences converging to zero. So these are just sequences of natural numbers converging to zero. This is a vector space where we are just looking at coordinate-wise addition. It has a norm, and you know, with respect to the supremum norm, this is a Banach space. You don't. It's just illustratory if you do not know much functional analysis yet. And the S of X is the unit sphere of the Banach space. So these are all the vectors that have norm 1. And this is related to a problem that was first conjectured that this would be true about many Banach spaces, but it turned out that really C0 is unique. And it has a flavor of Ramsey theory of finding something that's monochromatic, but because we are in the world of Banach spaces, which are continuous rather than discrete objects, and they, the void epsilons, then we are going to look for something that's epsilon monochromatic rather than monochromatic, and our coloring is not by finitely many colors, but by colors in compact space. So you can think of this as coloring this sphere by colors from the compact interval 0, 1 in a Lipschitz manner. So Lipschitz means that you're not too wild, or somewhat as if linear. And then you give me this epsilon that allows me to twiddle a little bit. So I'm not requiring that I'm going to be monochromatic. I'm going to be epsilon monochromatic. So the theorem says that there is an infinite dimensional subspace X of C0, such that if I look at the colors that it takes on the sphere of this subspace, then this is actually going to be within an epsilon long subinterval of 0, 1. And this is for every epsilon. With these approximate results, what happens is that this subspace actually depends on epsilon, right? So if I had that subspace for every epsilon, one single subspace for every epsilon, then I could as well have 0 there, right? So I would be really monochromatic. But the subspace, oh, and this should be X, sorry. This subspace does depend on the epsilon, and that's something you cannot get any better than that, right? So, but you see the analogy, and why I'm mentioning it, right? Of course, in spirit, it looks like a type of theorems that we talked about, but the proof, the combinatorial core, goes through ultrafilters. So he discretizes these colorings. And so he's looking at now all colorings are the Lipschitz functions, and instead of thinking about them as being continuous, he thinks about splitting the interval 0, 1 into intervals, right? So given the epsilon, right, you can find some n such that 1 over n is smaller than epsilon, and you split it into n pieces, and then he defines some operation, discretized version, that models scalar multiplication. And what he gets now with these with this discretization is a statement that actually resembles Heinmann's theorem, but it's a multi-dimensional version of Heinmann's theorem. So it's very closely related. Of course, there is a lot more work, and just the statement of this Ramses theorem takes some time, but basically this is what it is. You do the discretization, you have to include the what he calls a Tetris operation, and then use ultrafilters to find an analog of Heinmann's theorem. The proof is actually very beautiful. One other very interesting thing is that unlike the other theorems we talked about, this combinatorial result does not have a direct proof. So there has been a lot of effort to find a combinatorial proof without ultrafilters of this theorem, but there has been no success. Finite versions, yes, but not in the infinite realm. So I find it fascinating. And then there is density versions. So this is what we talked about at the beginning. They're more difficult to obtain. If I have a finite partition, then definitely one piece of that partition is going to have positive upper density, as defined here. But I could also split into finite Lemon pieces where each of them is going to have positive upper density. And then we are looking for an answer whether each of the pieces is going to have a certain pattern. And maybe we need a different notion of density. So here we're just using the density where we are looking at how large A is at the first and many elements of natural numbers proportionally to how many elements I'm looking at. You might also be familiar with Banach density, where you're looking not only with respect to the first and many elements, but you're allowed to look at all intervals of length n and look at how A looks there. So, but the results that I will mention, they work only with this upper density. So any suggestion of a set of positive upper density? What do you think is the density of the set of natural numbers?
1.
Yes. What about the set of evens?
Also 1.
So let's see how these numbers look like, right? So what if I have, well, okay, I put here 1, 2, that doesn't matter. So let's say that we start from 2, right? So I have 2, 4, 6, and so on. And then I'm measuring it with respect to 1, 2, 3, 4, right? So if I look at what goes into this limb soup, then I will have, well, if I just go over 1, then I have nothing. So that would be 0. Then if I go to 1, 2, then I have 2 in there. So I'll get 1/2. Then in 1, 2, 3, then I get 1/3, and then I get in here I get 1/2, and so on, right? So I cannot quite get close to 1, but I can get 1/2. And the same thing for odds. Here you see that what is important is the order, right? So on natural numbers, I have a given order. I can do this for other semigroups, and then it depends on the enumeration. So of course, if I enumerated natural numbers by having longer and longer intervals where I have even numbers next to each other, then I could reach the density 1. So it's but it's defined, it's density 1/2. So set that sort of doesn't have too large of gaps. So now Semeradi's famous result is that from the 70s, that was also originally proved combinatorially, and there was a lot of prelude in finding arithmetic progressions of length 3 and then 4. He proved that if I have a subset of positive upper density, then it contains arbitrary long finite arithmetic progressions. So density version of Thunderbirds Theorem. How it's relevant to us is that there is an ultrafilter proof that was done by Rustenberg. That takes too much time, but it's a lot shorter than Semeradi's proof. So again, very fascinating, and it was soon after Semeradi's theorem published. Then this that I mentioned at the beginning, these are winners of Fields medal. And we cannot use Semeradi's theorem because primes don't have positive upper density, but they are able to show that primes do arbitrary long finite arithmetic progressions by different methods, however. And then this is a recent result. I actually don't know which it was published. It appeared in the archive in 2019. These are 3 young guys working on ultrafilter dynamics, ergodic Ramsey theory. So they solved an old conjecture R dash that says that if I have a set of positive upper density, then I can find a sum set of 2 infinite subsets in there. So I can find 2 infinite subsets of natural numbers. So natural numbers, such that all pairwise sums from C are a subset of A. And definitely ultrafilters are heavily used in there together with some probabilistic methods. So this is very, very recent. And now we are open for questions.
Do you know of any applications of all this infinitary combinatorics in other, like places of mathematics and maybe physics as well?
Physics, I definitely do not know.
What about other mathematics?
So yeah, the Banach space theory, that's something that I am somewhat familiar with. And then, it's usually mostly that you're applying the ultrafilter approach for these patterns. So it's not too far off from what I talked about. You know, Ramsey phenomena in general, they just appear about everywhere, but then they are not necessarily in the realm of patterns in natural numbers, right? So you can get versions of Heinmann's theorems for arbitrary semigroups, but the meaning is not necessarily all that satisfactory, for instance. So there are versions of Heinmann's theorem that we would like to get, but then the ultrafilter approach does not really give you what you would want. So going to other dimensions even is not too straightforward. So it does sort of miracles in dimension one. You can do some miracles as with the Gauss theorem. Let me think. Or vice versa, that you're applying topological dynamics in the combinatorial number theory or this ultrafilter dynamical system, rather than I'm thinking that definitely the best person to look for references would be Terry-Tao and Green, who but I'm sure if they did something substantially different with it, then they are interested in problems about numbers.
I think I know that Terry-Tao has a lot of applications of Infinitary Combinatorics like this in his other work.
But he is really looking at things about natural numbers mostly, right? It can be general, and then measure can be in there, right?
Analysis.
There's ergodic versions of that, right? And then you can look at the things that are more complicated than these patterns that are polynomial patterns, but it's within the same area, sort of.
The theorem that you presented by Calvers is, I think it's really interesting. Is that the only? Did you say that that's the only continuous kind of thing that has been proved in this context? Or
right.
do you have other examples with continuous basis?
Yeah, with ultrafilters, I think that's the only one. We have a result about Banach spaces that's also a Ramsey result, but we use the dual Ramsey theorem. So it's not the same. For instance, we do not have an ultrafilter of the dual Ramsey theorem. So you can prove Hales-Jewett theorem using ultrafilters about variable words. And then you can use Hales-Jewett theorem to prove the Ramsey theorem. But I don't think that there is an ultrafilter proof of the dual Ramsey theorem directly, for instance.
Any other question for Dana? Yeah, so I think we don't have any questions from the floor. So thank you, Dana, for spending time and stay up so late to give us this lecture. Thank you once again. I'll see you again.
For waking up.
For waking up.
Those that are on the other side. Yeah, okay. If you have any questions, you can let me know on Saturday or anytime in between.
Yep.
Okay.
Okay. I'll see everyone.
Have a good day.
Again. Bye. Thanks, Dana.
Bye-bye.